Introduction to Machine Learning. So the machine learning can broadly be divided into two parts: supervised learnings and unsupervised learnings. Supervised learning is where the algorithms are trained using labeled input and output data which are used for future predictions. And unsupervised learnings is where algorithms are trained using unlabeled data to discover patterns in the data. Now the supervised learnings is used for future predictions. The dataset will contain historical features with historical labels. The features is same as variables, both dependent and independent variables. For example, a segment of text could have a category label such as spam versus legitimate email. So someone would have already gone through the data and marked the emails as spam or legitimate in advance. Then it could be positive or negative movie reviews. Using this historical data, the algorithm can learn and predict for the future data of the same kind, like for emails, whether those belong to the spam category or the legitimate category. So how it works? The network or the algorithm receives a set of input data along with the corresponding output data, and then the algorithm learns by comparing its derived output data with the actual output data to find errors. So if there are no errors, the model works, or if there are a lot of errors, then the model doesn't work. And it then modifies the model accordingly. Supervised learning algorithms are used in applications where historical data can predict likely future events. So how all of this works is the algorithm will use the data to form algebraic equations for each row in the dataset, with each column being an independent variable. It then solves that equation to find the coefficient for each of the independent variables based on the dependent variable as well, which is given as our output data. And then for future predictions, it will use those coefficients with the new input data and will find the corresponding output data for that. So here we have the machine learning process. The first step for that is data acquisition. So the data has to be acquired from somewhere. It really depends on the domain you are working with. Data can come from your customers, it can come from online databases, or even physical data coming directly from sensors, etc. But at some point it has to be acquired. The next step is data cleaning. So the data has to be cleaned and formatted, mostly using pandas library, so that there are no missing values or any other errors in the data, and the network would be able to process it. The data would then be split into training data and test data set, usually in the 70-30 ratio or 60-40 ratio. Then we will use the training data to fit a model on our algorithm for predicting outcomes given a certain set of inputs. Then we will test the model using test data and evaluate its performance by comparing its derived output with actual output in the test data. And based on our evaluation, we can go back and adjust the model parameters for better performance by trying to get a model which fits better on the test data. And then if we are satisfied with the performance, we can then deploy the model in the real world. Now this was a simplified approach to supervised learnings. If we are readjusting the model parameters, then the data should have been divided into three parts, as testing the readjusted model on the same test data would obviously show very little error, as the model was updated for better fit on that particular test data. So it isn't a test data anymore, it kind of becomes a part of the training data itself, isn't it? So the data should be divided in three parts, which is training data, validation data, and test data. The training data would obviously be used to train model parameters. Then the validation data is used to evaluate the model and then decide what parameters to adjust, and then test data for final testing of the model's performance. This means that after we see the results on the final test set, we don't get to go back and readjust any model parameters. This final measure is what we label as the true performance of our model to be, and we either deploy it or scrap it. We don't readjust the parameters after this. Now for learning purpose, we can do simple test train split as we won't be deploying the model in the real world, but that option is always available to us. Now next, let's move on to evaluating performance for the classification models. So some of the key performance metrics for classification are accuracy, recall, precision, and F1 score. Typically in any classification task, the model can achieve only two results. Either the model was correct or incorrect in its prediction. And all of these classification metrics stem from this idea only. So let's say in model evaluation. So for example, let's say in a classification task, we have a bunch of dogs and cat pigs with correct levels, and we need to classify this as either dog or cat. We train our model and then try to test a dog pig from the test split. So here, let's say we have this dog pig from the test image, and the correct level for this pig is given as dog. So we then pass that image through our trained model, and the model returned dog. Now we need to check by comparing it with the correct model whether this is the correct level or not. So dog is equal to dog, so that is the correct level. However, if the model returns cat, that would be incorrect. So there are only two possibilities. Either you are right or wrong, correct or incorrect. So if we repeat this process for all images in test dataset, we will end up with a count for correct matches and a count of the incorrect matches. But in the real world, not all correct and incorrect matches hold equal value. Therefore, we have different performance metrics for classification tasks such as accuracy, precision, recall, and F1 score. Now the first is accuracy. So accuracy is the number of correct predictions divided by total number of predictions. So for example, if the test dataset was 100 images and our model correctly predicted 80 images, then it would have an accuracy of 80%. Now accuracy is useful when target classes are well balanced. That is, we have roughly the same amount of cat and dog images in the test dataset. So let's say it will be in the ratio of 60-40. But imagine if we had 96 images of dog and only 4 images of cat in our test data, and in that case, if our model was simply a line that always predicted dog, we would still get 96% accuracy. So a model which always predicted dog no matter what, and 96 of the images were of dogs out of the 100 test images, then even that model would have 96% accuracy because it would be correct 96 times out of 100. But which is not right, because anytime a cat image comes out, it would be predicted as dog. It won't be able to recognize any of the cat images. So accuracy is a poor metric for unbalanced classes. So in this situation, we can use either recall or precision. So recall is the number of true positives divided by number of true positives plus number of false negatives. So true positives is if the model predicted, let's say the model predicted dog and it was indeed dog, the correct level was dog, so that is a true positive. If the model predicted dog but the pig was actually a cat, so that would be false positive. Similarly, false negative would be the model predicted cat but it was indeed a dog image, so it was false negative. We will talk more about this little later, but for now, recall is number of true positives by number of true positives plus number of false negatives. Precision is number of true positives divided by number of true positives plus number of false positives. So the only difference between these two equations is in the denominator. For recall we have true positives plus false negatives, and for precision we have true positives plus false positives. So recall is the ability of the model to find all relevant cases within a data set, that is of all the actual positive instances, how many did the model correctly identify. So of all the dog images, let's say there were 80 dog images and 20 cat images, then of the 80 dog images, how many were correctly identified? That is recall. And the precision is the ability of the classification model to identify only the relevant data points. That is, of all the instances which the model label as positive, how many were actually positive. So it doesn't want any negative values there. So for recall, imagine you are testing for a disease. So among a population of, let's say, 200 people or 1000 people, there are some infected people. We don't know how many, but you want to identify each one of the infected people. So you, in that case, you will have a high recall. You would want a high recall value, that of all the positive people, how many were correctly identified. And precision is every time it identifies something, it has to be correct. You don't want any false positives in that. So often we will have to decide on a trade-off between recall and precision, where increasing one will decrease the other. While Now remember, while recall expresses the ability to find all relevant instances in a dataset, precision expresses the proportion of the data points which our model says was relevant were actually relevant. Now this leads to an F1 score, which is the combination of both recall and precision. So F1 score is the harmonic mean of precision and recall. Harmonic mean gives less weightage to extreme large and small values as compared to the arithmetic mean. So what is harmonic mean? F1 is equal to 2 into precision into recall by precision plus recall. This is the formula for F1 for calculating F1 from precision and recall. Now we use the harmonic mean instead of simple average because it punishes extreme values. So a classifier model with a precision of 1 and a recall of 0 has a simple average of 0.5, because 1 plus 0 by 2 would be 0.5, but we'll get an F1 score of 0. So in the numerator we have precision into recall, so 1 into 0 would give 0. So the F1 score is able to, or the harmonic mean is able to punish extreme values here. So we can also view all correctly classified and incorrectly classified images in the form of a confusion metric. So in the confusion metric, we have x and y axis. On the x axis, let's say we have actual given condition, which is condition positive and condition negative. If we are testing for one of the conditions, either that would be positive or negative. And then this was on the y axis, and on the x axis we have our predicted condition, which is either positive. The image was, we were looking for dog images, and our model either predicted dog or it predicted negative, that is it predicted cat. So if you look at the matrix here, there are 4 possibilities. One is true positive, that is the condition was positive and the predicted value was positive as well. That is, the predicted value was positive and the condition was positive. Then we have false positive, which is type 1 error. Here the predicted value was positive but the actual value was negative. So it predicted dog, but actually it was a cat image, not a dog image. So that was false positive. This is called type 1 error. Then the model predicted negative and it was actually negative, that would be a true negative. But if the model predicted negative and the actual condition was actually positive, so we were looking for dog, the model predicted that image to be a cat image, but it was indeed a dog image, that is false negative. That is called type 2 error. Now we can use this confusion matrix and all 4 of these results, that is true positive, false negative and true negative. Using this we can calculate a lot of other metrics here, including our accuracy, our precision and our recall here. So recall is true positive by condition positive. Condition positive is true positive and false negative. So recall is true positive divided by true positive plus false negative, and precision is true positive by predictive positive. So precision is true positive by true positive plus false positive. If we go back, Precision is true positive by true positive plus false positive, and recall is true positive by true positive plus false negative. And we have that here. And there are other metrics as well. If you want, you can take a look. Now, the main point to remember with the confusion matrix and various other calculated metrics is that they are all fundamentally ways of comparing the predicted values with the actual true values for the test data points. So what constitutes a good metric will really depend on the specific situation. For example, is 96% a good enough accuracy for our earlier example? Well, there is no right answer, and it really depends on the context of the situation. So you have to ask some questions based on the context. That, let's say, did you create a model to predict the presence of a disease? Is that disease presence well balanced in the general population? Most probably not, right? Not everyone, not 100% of the population or even 50% of the population gets affected by any disease. So we need to decide if the model should focus on fixing false positive versus false negative. Often these models are used as a quick diagnostic test before having a more invasive test, that is getting a urine test before getting a biopsy. We also need to consider what is at stake here. For example, in a disease diagnosis, it is probably better to go in the direction of false positives. So to make sure we correctly classify as many cases of disease as possible. So in this case, if the model shows false positive, further medical testing can refute the presence of disease in the patient, which is better than getting false negative, that is not detecting the infected patient, which can be catastrophic like we had in the cases of COVID pandemic. And all of this is to say that machine learning is not performed in a vacuum, but instead it's a collaborative process where we should consult with experts in the domain, that is medical doctors in this case of diseases. So there is no single standard for performance metrics like accuracy, recall, precision, and F1 score. Everything really depends on the context and domain. Next, move on to the evaluating performance for regression models. Now, regression is a task when a model attempts to predict continuous values, unlike classification task where we try to predict categorical values. Metrics like accuracy or recall work only for categorical data where we predicted value can clearly be labeled correct or incorrect. So for example, let's say for regression model for consumer spending, if the model predicts a spending of $490 compared to the actual spend of $500, then how do we say if it was correct prediction or incorrect prediction? Therefore, we need separate performance metrics which are specially designed for continuous values. So the difference between regression and classification here is, let's say attempting to predict the price of a house given its features is a regression task, whereas attempting to predict the country a house is in given its features would be a classification task. So there are only 200 examples of country, and so that is a categorization. We are looking for category to put that into, so that is a classification task, whereas the price of house is a continuous values and that is a regression task. So let's move on to the regression evaluation metrics. We have 4 metrics here. We have mean absolute error, mean squared error, root mean square error, and R square, which is coefficient of determination. So the first is mean absolute error. This is the mean of the absolute value of errors. So mean, mean is average, which is sum of all values divided by number of values. Absolute is the mode of the value, so we turn all the negative values into positive values, and we have the error, which is the actual value minus predicted value. So it is easy to understand, but it doesn't tell us anything about the direction of the error, that is whether the predicted value was more or less than the actual value. So the mean absolute error is mean of the absolute value of errors. So we have the errors here. So we have, for all of the given values, we have y is the actual value minus y cap is the predicted value. So for each of the data points, we will separate the predicted value from the actual value, and it will return either a positive or negative number. So we will take a mode of that. So we'll take a mode of that to turn each of the errors into positive value, and then we will find mean of that, which is summation divided by number of values. So if you see here in this image, it's the same formula. Let's all of these blue dots are actual data points, and this red line here is the predicted value. It is the best fit line, and this gives us the predicted value. So y here is actual data point, this point, which is this point, and y cap is the predicted value for this, which is this point. So y minus y cap will give us this blue, dark blue line here. Similarly, for this data point, we have y cap, which is higher than the actual data point. So here we will have a negative error, and that's why we use this mode here to turn it into positive. So we find the error for all of these data points, and then we find the average of that, that is mean absolute error. Now the problem with mean absolute error is it doesn't punish large errors. Look at this 4 different data set here. We have x1 y1, x2 y2, x3 y3, x4 y4, and you can see these are 4 completely different data sets, but the line of best fit is exactly the same for all 4 of these. So for this one, it seems to be a good fit, with the mean error would be small value. But if you compare that with this and you try to predict, it won't give a very good answer, right? Because if you look at, for x value 8, we have many different y values, and this line is not predicting many different y values. For each of this y, it will give the answer here, which is something between 6 and 8, could be 7. So for every time you ask it to predict for x is equal to 8, it will reply y is 7. But we know the y varies a lot. So this doesn't really punish this large errors. Now this graph, this 4 images here, this is something called Anscombe's quadrate. So this Anscombe quadrate is a set of 4 different data sets that have near identical descriptive analysis and yet very different distribution. So if you look at all of these 4 images, the mean of x values, standard deviation of x values are all same. Similarly for y values, mean of y and standard deviation of y is same for all 4 of these distribution of data, and it has same correlation as well. So it shows that just the descriptive analysis is not enough to understand the data given to us. You have to actually look at the distribution in a graph as well to understand what data is given, because the mean of 3 and 5 is 4, and the mean of 2 and 6 is also 4. So now let's move on to mean squared error. So this is the mean of the squared errors. For those errors, we will square all of those values and then find the mean of those. So we'll take y minus y cap. Y is the actual value, y cap is the predicted value. We will find the errors for those and square everything. Here large errors are noted more than MAE, making MSE more popular, because let's say if you have an error of 2, the square of that would be 4, but if you have an error of 3, the square of that would be 9. So for larger errors, MSE will give us larger values. So using MAE for 2 and 3, the average, we would have gotten an average of 2.5. But here once you square it, the square of 2 is 4, the square of 3 is 9. So together they will give us 13 divided by 2, that would be 6.5. So MSE will give us larger errors. However, there is a problem. Squaring the error values squares the unit as well. So this is a problem. So for example, for the prediction of the house price, dollar will become dollar square, which is difficult to interpret and compared with the actual y values which are in the dollar unit. So to solve this, what we have is root mean square error, which is the root of the mean of the squared errors. So we have our square errors here. Either you write y cap minus y or y minus y cap, it won't make a difference once you square it, because the square of 2 is 4 and the square of minus 2 is also 4. So you find the errors, you take square of that and then average of that, sum all of that divided by number of points. This is the most popular evaluation metric as it punishes large errors, and at the same time it carries the same unit as y because we are using square root. So the dollar square will come back to the dollar figure. Now what is a good RMSE value? Once again, context is everything. Ideally you would want small error values, but a RMSE or root mean square error of $10 is fantastic for predicting the price of a house, which can go into hundreds of thousands of dollars, but it would be horrible for predicting the price of a candy bar. So you have to compare your error metric to the average value of the level in your test data set to try to get an intuition of its overall performance. But once again, domain knowledge will play an important role here as well, just like in classification, so it's important to talk to the experts in that field. Now last we have R square, which is coefficient of determination. R square is a number between 0 and 1 that measures how well the statistical model predicts the outcome. So R square can be interpreted as the proportion of the variation in the dependent variable which is predicted by the independent variables used in the regression models. A high R square value suggests a good model fit, meaning the model accurately captures the relationship between variables in the data. If not, if R square value is a smaller value, much more closer to 0, that would mean there, or maybe even if it's 50%, let's say it's 0.5, that would mean there are other independent variables which have not been considered in the model, which might explain the remaining variation in the dependent variable. So now at the end, let's take a look at the machine learning tree once again. So we have machine learning that is divided into two parts, supervised learning and unsupervised learning. Supervised learning has labeled input and output data and is used for future prediction. Unsupervised learning has unlabeled data, that is, it doesn't have column names, and it is used for pattern recognition among the given data. Now the supervised learning is divided into two parts. One is for categorical data, which is classification model, and then we have regression model, which is for numerical data or continuous data. The unsupervised learning is also divided in two parts. One is for clustering, the most famous of that is k-means clustering, and the other is for dimensionality reduction, which is principal component analysis. We won't go into the unsupervised learning for now, that part will come later. But for the supervised learning, we have performance evaluation metrics for both classification and regression model. For classification, we have metrics such as accuracy, recall, precision, and F1 score. And to evaluate the regression model, we have metrics like root mean square error and R square, which is coefficient of determination. So that's all for this video. See you in the next one with linear regression task. Thanks for watching.